Good day everyone and welcome. Today, we delve into the fascinating world of AI with our presentation titled Benchmarking General Purpose in-Context Learning. This groundbreaking research, led by Fan Wang, Zhuan Lin, Yang Cao, and Yu Kang, redefines and enriches GPICL, introducing innovative benchmarks that generate unlimited synthetic data. Stay tuned as we explore how this work not only pushes the boundaries of language modeling, but also paves the way for future advancements in AI. Thank you. Our research enriches and redefines the concept of general-purpose in-context learning, underscoring its importance to the AI community. We've introduced two innovative benchmarks. The first, meta-language, generates randomized yet consistent language patterns for meta-training. The second, Maze World, creates an unlimited number of tasks within randomized mazes, promoting context-based learning. However, we must acknowledge the limitations of current large language models. They struggle to handle the complexity of natural language that surpasses 8 gram and often rely on regularized and relatively monotonic visual signals for training, which are less complex than real-world scenarios. Despite these challenges, our preliminary investigations have yielded promising results. We've found that a completely randomized meta-language can train a language model to understand realistic natural language to a certain extent. This opens up exciting avenues for future research and development in the field of AI. As we delve into the realm of general-purpose in-context learning, or GPICL, we find it holds immense significance for the AI community. It's a topic that we've enriched and redefined, opening new avenues of exploration. Now let's consider the current state of large language models, or LLMs. These models are typically trained on specific existing languages, which presents a limitation. They often struggle when faced with the task of learning new languages. The figure here provides a comparison of GPICL and current LLM learning pipelines, illustrating the unique challenges and opportunities in this field. As we move forward, we'll explore how we can overcome these limitations and expand the capabilities of LLMs. The complexity of natural language is a significant challenge, as it far surpasses the 8 gram structure used in current models. This necessitates the development of models capable of handling higher complexity. Similarly, the visual signals in our current models are less complex than those found in the real world, indicating a need for models that can handle more intricate signals. Another issue we face is with synthetic data. While it holds potential, it's not yet validated for direct application, emphasizing the need for validated synthetic data. This brings us to the motivation for our new benchmarks. These benchmarks are designed to generate unlimited synthetic data, offering potential benefits to in-context learning, ICL, and general-purpose in-context learning, GPICL research. By addressing these challenges, we aim to push the boundaries of what's possible in the field of AI. In our research, we propose two innovative benchmarks, meta-language and Maze World. These benchmarks are designed to address the challenges we've identified in general-purpose in-context learning. The meta-language benchmark generates new languages using a randomized yet consistent pattern, while Maze World creates an unlimited number of tasks within randomized mazes. These benchmarks hold great potential. They can help us uncover more sophisticated models and optimization techniques. For instance, we've used the Noam decay scheduler to optimize the meta-language and Maze World baseline models. This scheduler peaks at a learning rate of 10⁻³ after an initial warm-up phase of 1,000 steps. In essence, our work is a step towards understanding and enhancing the capabilities of AI models in learning and navigating through complex, unpredictable environments. We believe these benchmarks can significantly contribute to the research of in-context learning and general-purpose in-context learning. Our research introduces two innovative benchmarks, meta-language and Maze World, specifically designed for general-purpose in-context learning, or GPICL. Let's delve into meta-language first. This benchmark creates a randomized yet consistent language pattern. It's designed to generate new languages, providing a unique way to assess a model's ability to learn. This pseudo-language is simulated using n-gram settings, which means the probability of the next token is determined by its preceding n tokens and a set of random parameters. What's fascinating about meta-language is its adjustable complexity. By manipulating the size of the vocabulary and the n parameters, we can make the complexity of the pseudo-language arbitrarily high. This allows us to test super long-term dependencies, pushing the boundaries of what our models can learn and understand. In essence, meta-language provides a robust and flexible platform for evaluating the learning capabilities of AI models in a controlled yet challenging environment. Diving deeper into our research, we've developed a unique approach called Maze World. This technique generates an infinite number of tasks within randomized mazes. The model is meta-trained through context, allowing it to learn exploration and navigation. Each step in time is represented by a pair of tokens, adding another layer of complexity to the learning process. Now let's talk about our training methodology. We've optimized our benchmarks using a strategy known as the Noam Decay Scheduler. This scheduler starts with a warm-up phase of 1,000 steps and then peaks at a learning rate of 10 to the power of -3. This approach ensures a steady and controlled learning process, which is crucial for the success of our models. In summary, our research proposes a novel approach to in-context learning, combining the complexity of Maze World with an effective training methodology. This combination has the potential to significantly advance the field of general-purpose in-context learning. Our research design involved conducting limited experiments with baseline models, using specifically designed benchmarks. These benchmarks serve as tools to uncover more sophisticated models and optimization techniques, thereby extending the horizon of general-purpose in-context learning. Moving on to our technical results, our preliminary investigations have been quite promising. We found that a completely randomized meta-language can be used to train a language model. This model, interestingly, is capable of understanding realistic natural language to a certain extent. This discovery opens up new possibilities for the application of AI in language modeling and indoor navigation. However, it's important to note that the synthetic data generated by these benchmarks are not yet validated for direct application. In summary, our research has taken significant strides in the field of in-context learning, and we're excited about the potential of these findings to shape future AI applications. Our research has led to some key results. We've introduced two benchmarks, meta-language and Maze World. Meta-language uses a randomized language to train models, helping them understand realistic language to a certain extent. The Maze World, on the other hand, shows potential applications in language modeling and indoor navigation. However, it's important to note that the synthetic data generated from these benchmarks are not yet validated for direct application. Moving on to the implications of our results, these benchmarks show great potential to benefit in-context learning and general-purpose in-context learning research. Our findings highlight the complexity of natural language and underscore the need for advanced models and techniques. Looking ahead, this work can be expanded by developing more realistic GPICL benchmarks and more sophisticated models. This will help us further extend the GPICL horizon and enhance performance gains. In our research, we've redefined and enriched the concept of general-purpose in-context learning, or GPICL, highlighting its importance to the field of artificial intelligence. Our focus has been on developing benchmarks that can generate unlimited synthetic data. As you can see in the figure, we've evaluated language models of varying sizes on the meta-language benchmark with different complexity levels. This is a significant step towards understanding how these models can learn and adapt to new languages and tasks. We believe this work opens up new avenues for the development of more sophisticated models and optimization techniques, ultimately extending the GPICL horizon and enhancing performance gains. We've introduced two benchmarks in our study. The first, meta-language, uses a randomized language pattern for meta-training. This allows models to learn a new language from scratch, a significant step forward in in-context learning. The second, maze world, generates an unlimited number of tasks within randomized mazes. This unique approach allows the model to learn exploration and navigation solely through context. Our preliminary results are encouraging. The randomized meta-language shows promise in training language models. We've also seen potential applications in areas such as language modeling and indoor navigation. However, it's important to note that the synthetic data generated by these benchmarks have not yet been validated for direct application. We also acknowledge the challenges and limitations of our work. The complexity of natural language far surpasses what our current models can handle. Additionally, the visual signals used in training are less complex than those found in the real world. These are areas we aim to address as we continue to refine and expand our research. Looking ahead, we see two key avenues for expanding this work. Firstly, we aim to develop more realistic GPICL benchmarks. This could involve adding greater complexity to the meta-language, thereby pushing the boundaries of what our models can learn and understand. Secondly, we plan to uncover more sophisticated models and optimization techniques. This could involve exploring long-term dependency modeling or reinforcement learning, which could further extend the GPICL horizon and enhance performance gains. In terms of optimization techniques, we've already made strides with our meta-language and maze world models. These have been optimized using the NOEM DK scheduler, which peaks at a learning rate of 10-3 following an initial warm-up phase spanning 1,000 steps. This approach has proven effective in our preliminary investigations, and we're excited to see how it can be further utilized in future research.